In this lesson, we'll continue to talk about consumer mathematics and financial management. And there's a reason why this is subtitled Planning for Retirement Now. And as we go through these examples, you'll see the reason why it is so important for you to plan for retirement savings as early as you possibly can. In this lesson, our objectives will be regarding annuities. Number 1, determine the value of an annuity, and number 2, determine what the regular annuity payment should be in order to achieve a particular financial goal. So let's look at some examples of annuities. Here's our first example. Lynn is saving $1,200 per year in an account that will earn 8% annual interest. If she continues to do this for 20 years, how much will she have in her account? Another example. Roger recently had a winning lottery ticket that promises to pay him $1,000 per month for 30 years. Roger has a good job, so he plans to put all of this money in savings for his retirement. How much will Roger's retirement account contain when he retires in 30 years? And the last one. Keisha wishes to have $1 million in her retirement account at age 62. Keisha is now 22, so she has 40 years to make this happen. She plans to make equal payments at the end of each month. If her investment earns a 6% return annually, how much does Keisha need to deposit each month to achieve her goal? If Keisha waits until she is 32 to start, how much does each deposit have to be? And what if she waits until she's 42? And I think this last example will help you to understand why it is so important that you plan for your retirement at the earliest age you possibly can. So in these examples of annuities, there's one particular characteristic that actually makes it an annuity. Notice in the example about Lynn that there is a savings of $1,200 per year. In the example about Roger, it's $1,000 per month. And in the last example with Keisha, equal payments at the end of each month. And so that's how you recognize that a problem is describing an annuity. The unique characteristic that defines an annuity is the presence of regular payments over regular intervals of time. So that is depositing or withdrawing the same amount of money according to a specific schedule, such as $1,000 a month for 10 years. This regular payment over specific regular interval of time, the fact that you're making the same payment amount at the same time every time for a certain period of time is what makes an investment an annuity. So we have several formulas associated with annuities. You do not need to memorize these, but you do need to be able to recognize them. This is the value of an annuity with annual deposits. So if P is the regular payment made, and it's made at the end of each year, for an annuity that pays an annual interest rate R, compounded once a year, the value A of the annuity after T years is given by this formula. So the variables in these formulas are very similar to the variables we've seen in our previous formulas. We've got our P, which is going to be, in this case, a regular payment. We've got an R, which is an interest rate. We've got time. This time it's in years. And we've got A, the amount that we'll have at a certain time. So very similar to the other formulas we've been seeing. So since Lynn is saving $1,200 per year in an account that will earn 8% annual interest, Lynn is investing in an annuity that has annual deposits. $1,200 per year in an account earning 8% interest. So let's answer some questions about Lynn's investment. Part A, if she continues to do this for a period of 20 years, how much will she have in her account that she can use in her retirement? Part B, how much did Lynn actually pay in over this 20-year period? And part C, how much did she actually earn in interest during this 20 years that she was making these deposits? So we've got our formula. And we need to identify what the specific values are for the variables in Lynn's case. And we know that Lynn is investing $1,200 per year. And in addition to that, we know she's going to earn 8% interest. And we know that she's going to leave it for 20 years. So we know our R is 0.08. Our P, or regular payment, is $1,200. And we know that the time is 20 years. So we can put all of this information into our formula. Now, I'm going to want to do this in the calculator, and so are you, because it's very tedious, obviously, to do this by hand. But let me write it out the way it would be written in the formula first, and then we'll switch over to the calculator. The amount that we have is $1,200. 1 plus our 8% interest rate. That's all in parentheses, raised to 20 years. Subtract 1. All of that is divided by the interest rate, 0.08. So what we want to do is we want to enter this in the calculator, and I'm going to go ahead and give you one hint that's going to help you in entering this in the calculator, especially in some of the later problems. We need to put parentheses around our denominator and parentheses around our numerator, even though those are not given in the formula. So now I'm going to switch over and use my calculator. And I'm going to enter this in my calculator just as I see it here. Left parentheses, 1,200. You could put a bracket, or you can just put another parentheses. And then another parentheses, because notice that there's a bracket and a parentheses, so I need two of those symbols here on the calculator. 1 plus 0.08, close those parentheses, raise that, use the caret key, to the 20th power, subtract 1, close the bracket, close the parentheses, divided by, and in parentheses, 0.08, close parentheses. That gives me an answer of $54,914.36. As you can see here on the calculator, if we round it to the nearest penny, that's how much we'd get. Now, since you're most likely to make a mistake when you're entering it into the calculator, because if you don't remember to put those extra parentheses in the places where I've indicated, you're going to miss it. So because of that, I'm going to show you a way that you can break it down, and it will make it less likely that you make a mistake on the calculator. So we're going to start out exactly the same way and enter our parts that we know into the formula. So there's our regular payment. 1 plus 0.08 to the 20, subtract 1, all over 0.08. And I'm going to start simplifying this by following the rules for order of operations. Those are the same rules for order of operations you've probably learned in other algebra courses. That tells us that we do what's inside of the grouping symbols first. And inside our grouping symbols, we can add 1 to 0.08 to get 1.08. And now comes a time when we are going to have to use the calculator, because you do not want to multiply 1.08 times 1.08 times 1.08 20 times. So I've got to do what's inside my grouping symbols. Remember, I'm following order of operations. It says do all the grouping symbols first. And in there I've got an exponent and a subtraction, so I need to do the exponent then the subtraction. So this part, 1200, is going to stay the same, and 0.08 is going to stay the same. And I'm going to get a value here for what's in those parentheses or brackets, and I'm not going to be able to find that value exactly. It's going to have too many decimal places in it. So what I'm going to do is I'm just going to write out as many decimal places as the calculator shows me, and if you do that, you won't get a rounding error. So I'm just doing the part in those brackets, 1.08 to the 20th power, subtract 1, and the calculator will do that in the right order. It will raise it to the exponent and then subtract 1. And so you see I get this value that has a lengthy decimal, but that's okay. I'm just going to write out 3.6609 57144. So I am taking the exact number I see on the calculator, and I'm not rounding. Now you could probably round it to 4 or 5 places and be accurate to a penny, but just to be safe, because you know how it is with the technology, it will only accept that exact answer. So to be safe, if you'll write down all those decimal places, you'll be fine. So now I have multiplication and division, right? I have multiplication here. That's what the parentheses means. I have division here. That's what that bar means. And that's done from left to right, or you could do the top divided by the bottom. In either case, you're going to get exactly the same answer, because if we go left to right, the top's going to get done first and then the bottom. So now I'm going to go ahead and do this in the calculator. Now, I don't know why, but when I click on this, that 3.660957144 is going to disappear, but you'll be able to see it on the calculator screen. So it's 1200 times, and you can use the times symbol or the parentheses, which mean to multiply, 3.660957144. And notice how carefully I entered every single digit from that number that shows on the calculator, divided by 0.08. And we get the same answer that we saw just a few minutes ago, and that's the $54,914.36. So practice with your calculator. Even though you don't have to memorize the formula, you may miss this on the proctored exam, for example, if you don't know how to enter it in the calculator. So you've got to be really careful about that. Now, there were some other parts to this Lynn problem that we wanted to answer. So I want to go back and look at the other parts. So how much did Lynn pay in over this period of time, and how much did her account actually earn? So if we want to go back and answer this part B, we know that Lynn made $1,200 payments every year for 20 years. So that means she put in $24,000. But at the end of time, at the end of the 20 years, we just found that her account was going to be worth $54,913.36. So if we take away the amount that Lynn actually put into the account, we find out that because Lynn has made this investment, earning this money over time, that she earned more than she actually put in. She earned over $30,914.36. So now we're going to look at an annuity that includes payments by the month. Roger recently had a winning lottery ticket that promises to pay him $1,000 per month for 30 years. Since Roger already has a good job, he plans to put the money in savings for retirement, and if he continues to do this for 30 years, and the return on the investment is 2.5% annually, how much will Roger's retirement account contain when he retires in 30 years? So our formula looks very much like it did before, only this time we have payments per month. So we have an additional N in our formula because N was one payment in the previous formula, so we didn't have to have that value 1. Because we've introduced this, we're going to have an even more difficult expression to enter in the calculator because, as I told you before, you need parentheses around the numerator and denominator, and you need parentheses now also around the exponent because it contains an operation. Now, if you're comfortable entering it this way, that's fine. Just be sure you put all those parentheses in. But if you've tried some of these and you've been having trouble getting it right, it probably has to do with the way you've entered it in the calculator. So I'm going to show you how to break it down into smaller pieces. So as always, our first job is to identify the values we're going to put in our formula. So we've got $1,000 a month. We've got a rate of 0.025 because that 2.5% decimal moves back 2 places to the left. We've got a time span of 30 years, but this time we also have monthly payments, monthly compounding going on. So we've got to substitute all these values in our formula and then enter it into the calculator correctly. So when we enter these values into this formula, we get 1,000, and then there's a bracket, 1 plus our rate, 0.025, divided by 12. That's raised to the n times t, or 12 times 30. Subtract 1, that's our numerator, divided by our rate, 0.025, over our n, which is 12. So the easiest way to do this in the calculator is to take it by the grouping symbols. And the calculator will do it in the right order within the grouping symbols that you see. So we've got the 1,000, and then we're going to get a number for that value in the brackets, and we'll get a number for that value in the parentheses. And once we get those numbers, we'll be able to find our final answer. So I'm going to do it in the calculator first, and then I'll write in the numbers. So I'll start with the numerator, parentheses, 1 plus 0.025 divided by 12, close parentheses, raised to, in parentheses, 12 times 30, or you can multiply that out and get 360, and you don't have to put those parentheses. Subtract 1. I get a value of 1.11349048. In the denominator, 0.025 divided by 12, and I get a value of 0.002083333. So I can take my 1,000 times the expression we got for the numerator, the 1.115349048. I use parentheses for multiplication, so I need to close those parentheses, divided by the number we got for the denominator, 0.002083333, 5 threes, and I will get the answer to my problem, $535,367.55. Final answer of $535,367.55. That's the amount that Roger would save by putting that $1,000 into his account every month for 30 years. Now let's take a look at an example that will sort of demonstrate to you the importance of investing early for retirement. Keisha wants to have $1 million in her retirement account at age 62. Keisha's now 22, so she has 40 years to make this happen. She plans to make equal payments at the end of each month. If her investment earns a 6% return annually, how much does Keisha need to deposit each month to achieve her goal? If Keisha waits until she's 32 to start, how much does she have to deposit? And if she waits until 42, how much does she have to deposit? And those are monthly deposits. So this time we're looking for the amount of the payment, and our formula has been solved for P, which is going to be the amount of the payment. And we need to know the values of these other variables in order to solve the problem. And all of that information is given to us in the problem, so let's write down what they are. We know that the amount she's looking for is $1 million. We know that the rate she expects to get is 0.06. That right now she's 22, so that will give her 40 years to make those monthly payments. That's our N, 12 for months. And so we know every variable except for P, the amount of the payment. So we can use these values in our formula to find the amount of the payment. Now we've got to be really careful with our parentheses again. So I'm going to suggest to you that you do the numerator and the denominator separately, and that you don't try to do this all in the calculator at one time. So we've got our $1 million. We've got our 40 years. We've got our 12 payments a year. We've got our interest rate of 6%. So those are our values for A, T, N, and R. So in the numerator, we're going to have to do $1 million times 0.06 divided by 12. So I'm going to do that part first on my calculator. It's 1 million times, in parentheses, 0.06 divided by 12. That gives me a numerator of 5,000. Now I'm going to go ahead and do the denominator. So that denominator is going to be bracket 1 plus 0.06 over 12 raised to the 40 times 12, subtract 1, and I'm just going to remind you about those parentheses around that exponent, or go ahead and do NT as 480. Just going to take my calculator and go ahead and calculate that part. Parentheses 1 plus 0.06 divided by 12, close parentheses, raised 2. You could go ahead and put 480, or just remember, put parentheses around that, 40 times 12. All of that, subtract 1. That gives me a denominator of 9.957453672. So to get my final answer for, and by the way, I'm looking up here, and that needs another 0. That's not a million. 1 million has 6 zeros. Last step, do the division. 5,000 divided by 9.957453672, entering very carefully, because you will get a rounding error if you do not watch what you're doing here. And there's our final answer. Keisha's going to have to deposit $502.14. Keisha's got to put that $502.14 a month away, and then she'll be a millionaire when she's 62. Now that might seem like a lot of money to put aside, and it is, but watch what happens when Keisha waits until she's 32 years old to do this. So much of the problem is exactly the same. She still wants the $1 million. She still has a rate of 6%. She still has 12 monthly payments, but this time her time is now 30 years instead of 40. Because if she waits until she's 32, there'll be 30 years until she's 62, between 32 and 62. So, same kind of process, enter in the calculator, and I will let you enter it in the calculator, but let me tell you that you should get 5,000 in the numerator, 5.022, 575,211 in the denominator, and that turns out to be a payment of $995.51. So instead of about $500, she's got to put almost $1,000 a month. Now, if she waits until age 42, it's even worse. Because at age 42, time is not on her side anymore. She still wants $1 million. She's still getting a rate of 6%. She's still paying 12 monthly payments. This time, her time has been cut to 20, because it's 20 years. So again, enter in the calculator, and you should get 5,000 over 2.310204476, and when that's calculated, if she waits to age 42, she has to put $2,000 a month in her account for 20 years in order to guarantee herself that $1 million for retirement. So look what happens if she delays making these retirement payments. That's why it's so important, even if you can only put $20 or $25 a month away, that you start saving for retirement early so you have time on your side. Because with the effects of the compound interest over a longer period of time, you're going to earn so much more interest. In fact, let's take a look at how much Keisha pays in under these three circumstances and how much Keisha actually earns in interest in these three circumstances. So we had a 40-year investment, we had a 30-year investment, and we had a 20-year investment. So over 40 years, she had 480 payments, because that's 12 times a year for 40 years, or 12 times 40, 480. 360 payments, 30 years times 12 for the 30 years. And if she waits to age 42 and she only has 20 years, she's only making 240 payments. Now you might say, well, that sounds great because she's not having to make as many payments. But remember, her payments get higher as she waits to start investing. 502.14, 995.51, and $2,164.31. So to figure out how much Keisha actually has put in of her own money, we have to multiply these numbers times the number of payments. And we'll know how much Keisha actually invested. So in the case of the $502.14 a month, she puts in $241,027.20. In the case of the 360 payments or 30 years, she puts in $358, $383.60. So in the case of the 20 years, she actually puts in $519,434.40 of her own money. So you can see that she's increasing the amount that she's having to put in order to get the $1 million. So if you take the $1 million and you subtract each of these values, you're going to see that she really has let her money work for her if she starts earlier. She earns $758,000 if she starts at age 22. She's still got $1 million, but she only put in $241,000 of her own and earned $758,000, almost $759,000. If she waits till she's age 32 and only has the 30 years, she puts in $358,000, which means she earns only $641,616. She's had to put in over $100,000 more in order to get that same return because she waited 10 years to get started. And in the last case, of course, that's the worst case scenario. She had to put in over $500,000, so her money's only earning $480,565 and some change.